Any questions on the homework? We do, our exam, second exam is the 10th, so 1 week from today. All right, then we sort of started 8.9, looked at a couple of improper integrals, both of which were divergent. So both scenarios were covered here. We looked at a unbound region of integration, and example 5 was improper because we were integrating across or up to the vertical asymptote. So both of those diverged infinite area. Were there any questions on either of those two? All right, so the limit technique is really what's new here. And you know, like with most of these, the issue is figuring out how to find the antiderivative. So we'll look at this 1 over x squared from negative infinity to 1. We're going to compare that to the two examples we just did, which were 1 over x. But when we see something like this, we want to identify the piece that's making it improper and relabel that as something. So we're going to relabel this as the integral from a to negative 1, and then let a go to negative infinity. Really, the choice of letter there is totally up to you. Okay. And the limit as a approaches negative infinity, or the limit on all of these, is the last thing we apply. So we're just going to keep this out front until we have the antiderivative in terms of a. So the antiderivative of 1 over x squared would be what? Negative 1 over x. And we're evaluating that from a to negative 1. So again, we're still going to evaluate this first, and then compute the limit. So still the limit here. Plugging in negative 1, we get 1. And plugging in a, so f of b minus f of a. And then we're going to compute the limit as a approaches negative infinity. So we'll just call that a plus. Get rid of this. So what happens here? As a approaches negative infinity, we get yeah, 1 over something getting larger and larger is 0. So this is equal to, yeah, just 1.
Sorry, I thought you were asking about 1 over 8.
Oh yeah, that would have worked too. That approaches 0. So in the instance of this function, just looking at it visually, we have a finite answer, a finite number, which is a convergent. There's our function. We'll look at it. There's 1 over x squared from 1 to negative infinity. And what we're saying is that this area here is finite. It goes way up here. Area is 1.
Negative to negative 1.
Negative 1. So if we compare that to the previous example where it was just 1 over x, we saw both that situation was divergent. This one with 1 over x squared is convergent. So it's sort of the way you're thinking of it, I guess, is how quickly does that tail die off? So with 1 over x squared, it decreases towards 0 much more rapidly than like 1 over x does, and then that's sort of the aspect that's giving us infinite versus a finite area. Okay, does anyone have any questions on that? Okay. So the example 7, the improper piece is now the upper limit of integration. We'll just call that b. And we've got to compute the limit as b approaches infinity. Our function 1 over x squared plus 49. So how do we find the antiderivative of that? Trig substitution? Yeah, trig substitution would work. Is there something more efficient? It's the inverse tangent, right? That's inverse tangent form. Specifically, our antiderivative is what? Yes. 1 over 7 inverse tangent of x over 7. So you can certainly do a trig substitution there, it's just not as efficient. You get the same result. I feel strongly that you should recognize the integrals for inverse tangent and inverse sine. Okay, so plugging in b. Minus plugging in 0. And then computing the limit as b approaches infinity. Sorry, that's an inverse tangent there. Our argument of b over 7. b approaches infinity. Okay, inverse tangent of 0 is 0. Tangent of what is 0? Tangent of 0 is 0. How about as b approaches infinity, what happens here with the inverse tangent of b over 7? Yeah, pi over 2. So inverse tangent looks something like that. Here are your 2 horizontal asymptotes. Here and here at pi over 2 and negative pi over 2. So what we have is, we'll just write it here. This approaches pi over 2, and this approaches 0. We have pi over 14 minus 0. So again, we've got a finite number coming out of that unbounded region of integration. Okay. Anyone have any questions on that? All right, so why don't y'all try example 8. Yeah, I don't think I would care either way. saw either use substitution or partial fractions, both actually turn out to give you the same result. So either method totally valid here. We went partial fraction route. You know, what you can do is just figure out the antiderivative first and then plug all this stuff back in instead of, you know, carrying this over and over and over again. So we could come back up to this once we evaluate this antiderivative. Just kind of off somewhere off to the side. Okay, so there's our partial fraction. You end up with the same result with a u substitution as well. So we have natural log, absolute value of x plus 2. And we have a, you know, you might use substitute here, but since we have x plus 2, the derivative of that thing on the inside is just 1. So you don't really need to worry about any like weird multipliers or dividing things with that x plus 2 as your argument. So plus 2 over x plus 2 to the first. All right, there's our antiderivative, so we'll just kind of separate this from the rest. And then we need to compute the limit, or we need to evaluate our antiderivative from 2 to b, and then let b go to infinity. Let's rewrite this here. Just kind of starting over. So I would recommend, like, don't just glance at this stuff and say, all right, well, that first one's going off to infinity. That means that everything is going to be divergent. You know, like, maybe you can see that here is the case, but oftentimes these things do evaluate or could evaluate to something that's indeterminate, and at which point you couldn't say one way or the other whether it converges or diverges. So just be really careful before you say all this is infinity, that you actually are thoroughly convinced, or that you can thoroughly convince someone that it is actually infinity. Okay, so we're going to plug in b. Minus plugging in 2. And then we're evaluating as b goes to infinity.
That should be b plus 2.
So it should be 2 over
Yeah,
4.
it's
Oh, it's
This
2
one
right here,
has-
isn't it? Yeah, thanks. Sorry about that, thank you.
doesn't
So
really change a
2/3
whole
would
lot,
be 1/2.
but you know.
Eh?
The
Oh, yeah.
2/3.
It changed this to 2/4 or 1/2. So this is, we see that like infinity minus infinity wouldn't be the case here because this is some finite number. This is finite. As b approaches infinity, this is the natural log basically of infinity. We know natural log goes off to infinity. So that's infinite. 2 over b plus 2 as b goes to infinity. Again, that's approaching 0. So, you know, what we have is infinity for that first parentheses. Oops. And then subtracting a finite number is still infinite. Yeah, it's just this minus some finite number. Again, if that were infinity minus infinity, you've got to do L'Hopital's rule to figure out what that limit actually is. So as long as it's something like this, we can rest assured that it is infinite. And that this diverges. Or divergent. Does anyone have any questions about that? All right, a couple more. So the antiderivative for number 9, x cubed over x to the 4th minus 1. How are we going to find the antiderivative? So think about it for a minute.
Derivative of the bottom to the top. So you just multiply it by 3, and then you do the natural log of
Okay, yeah.
minus 1.
Right, it's almost in logarithmic form. You might see, well, all right, well, it's definitely a proper fraction. So x to the 4th minus 1, difference of squares again. You could break that down into 4 linear factors. But it's easier to recognize that that is almost in logarithmic form. We multiply the top by 4, and we divide by a 4th to evaluate that. The improper portion comes from our 1. So we need to compute the limit as b approaches 1 from what direction? From the left. Right, our interval goes from 0 to 1. The only way we can approach 1 is from the left. Okay, so limit as b approaches 1 from the left. We have our x cubed over x to the 4th minus 1. The derivative of the bottom is 4x cubed. So if we had a 4 here, then our integrand's in logarithmic form. But to put the 4 there, we need a 4 here. And a log form is just like a shortcut for u substitution, basically. So we've got 1/4 limit as b approaches 1 from the left of natural log absolute value x to the 4th minus 1. So do we need the absolute value here, or can we get rid of them? Need them. If you're unsure, just leave it. There's never any harm with leaving it. We're in the interval from 0 to 1. These fractional things cubed minus 1 are negative numbers. So we need it there. Okay, so it's 1/4 natural log of, evaluated from 0 to b. Forget that. So we have b to the 4th minus 1 minus ln of negative 1. All of that, and then we pull our constant out. So as b approaches 1 from the left, what do we get? Basically, it turns into the natural log of 0. In terms of a limit, though, what is the natural log of 0 approaching 1? So let's write it out. The natural log of the absolute value of -1, that's 0. That other part's 0. This is, you know, symbolically, it's like we said, this turns into the natural log of 0. But this is in the context of a limit. It's not that we're saying evaluate the natural log of 0, right? So I think that notation is a little bit misleading. But as we approach 0 on the natural log function, or the natural log looks like that, there's 1, 0. Natural log approaches as we approach 0. Negative infinity. So in the sense of a limit, that's 1/4 times a negative infinity, which is negative infinity diverges. So based on how we've rewritten our integral, the integrand is not defined when x is equal to 1. So on the function x cubed over x to the 4th minus 1, you're going to have a vertical asymptote there. So we're integrating from 0 to the vertical asymptote from the left. So I don't know, something looks something like this. I'm not sure where it's at, but you know, we're finding this area here. All right, that's infinite based off of our work. Like I said, the notion of this convergent divergent stuff directly plays into sequences and series. So the entire next unit is developed around the notion of expressing functions as an infinite polynomial. And so if something converges, then we can say, well, this function, like maybe this exponential function, converges to this polynomial. So instead of integrating an exponential function from 0 to 1, we can integrate that polynomial from 0 to 1. And it's beneficial because there's an instance, multiple instances of when you have a function that doesn't have a known antiderivative, like e to the x squared. So when we say like a polynomial converges to e to the x squared, that means we can write e to the x squared as an infinite polynomial, and we can just integrate the terms of the infinite polynomial instead of a function that doesn't have an antiderivative. Okay, so this is a very important notion that we see coming up. Example 10, we've got 1 over root 36 minus x squared. How would we evaluate the antiderivative? Trig sub? Yeah, trig sub could work. Or we could recognize that it's the inverse sign antiderivative, right? So again, issue being not the 0, but the 6 in the upper bound. So we're going to call that b. From 0 to b, we've got to compute the limit as b approaches 6. From what direction? From the left, once again. Left. Okay. So So that is, it's already in the form basically for the inverse sine. So you've got a equals to 6. We did a trig substitution like this one in 8.4. I think it was identical. I think it was the exact same problem without the bounds. Okay, so it's just the inverse sine of x over 6. From 0 to b. So as b approaches 6 from the left, we have inverse sine minus inverse sine of 0. So this is b over 6 here. Okay. Inverse sine of 0 is 0. As b approaches 6, inverse sine of b over 6 approaches what? Pi over 2. So that's basically the inverse sine of 1. Sine of something gives us 1, sine of pi over 2. You know, other values too, but oops, you gotta remember that the inverse sine's range is restricted. It's pi over 2 minus 0. Pi over 2 is the answer.
What's its range or domain restricted to?
The domain for inverse sine?
Yes.
Does anyone remember the domain for the inverse sine?
0 to pi.
0 to pi. That's the range for inverse cosine.
Is it negative pi halves or pi halves?
That's the range of inverse sine. So inverse sine will output angles from negative pi halves to pi halves. But it takes in numbers from -1 to 1 inclusive. Yes, so like where the inverse sine comes from is just the sine function. Right, we have this sine function. You had to make, in order to have an inverse function, you have to make that 1 to 1. And so sine is restricted from here to here, just so we have positive and negative values. You can really restrict it wherever. You just want whatever you're restricting, you just want it to pass a horizontal line test, so it's 1 to 1.
So it's just by convention what it's restricted to, right?
Correct.
Okay.
Yeah.
So if for some reason we're doing a problem where the limits were outside of the range, the domain of this function,
Mhm.
could you redefine the domain if it's arbitrary or no?
Well, no, because the range of sine is the domain of the inverse, and the range of sine is always from -1 to 1.
Okay.
So you can't
Okay, yeah.
change that domain.
Okay, that makes sense.
But you can change the range. Like if I chose like a different branch of sine, if you will.
Yeah.
Like if I chose this branch of sine over here, then my input is still from -1 to 1.
Yeah.
But my output is different.
Because it repeats itself every 2 pi or whatever.
Yeah.
Okay.
Yeah. Right.
So how about if we have the limit from to the infinity of the sine?
The limit where at infinity
Yeah, of the sine x.
of just sine x.
Yeah.
Yeah. So what is that limit?
It's 1.
Is it 1? Or is it -1? Or is it
Both.
neither?
Either.
It doesn't, it's undefined.
It's undefined.
So in this context, is being undefined different from converging to infinity or negative infinity?
Yeah, so like in this context,
Yeah.
when we say this is undefined, what we really mean is that it doesn't exist. And even limits at infinity don't exist either, right?
But they don't exist in a different way.
Right, and in this context, we're saying that, you know, the limit is showing up, but it's showing up to describe what happens as we get closer to an asymptote or further and further out. In an instance where it's just the limit as x approaches infinity on the sine function, another way to remember or to think about limits at infinity is the end behavior. So like if you take anything and put a limit at infinity on the front of it, you're asking like over you know, a vast amount of time, how is that thing gonna behave? Is it flattening out? Is it going off to infinity, or is it going off to negative infinity as we progress? Or is it doing neither one of them, like in the case of sine or cosine? So, you know, sine is just always doing this, right? So like, if you say it's 1, that's not true, because way out here, it's 1, but even further out, it's negative 1, and even further out, it's 1 again. So that we say that limit doesn't exist. Because it's not, the function's not like flattening out. Like a limit, you know, you can have a periodic function like, you know, like say this were 5. You could have a periodic function that's kind of oscillating like this, and then it flattens out. So, you know, we could say that that limit at infinity does exist, and it's 5. But for sine and cosine, the limits at infinity don't exist. Yeah, thanks. Any other questions? Yeah.
So if sine x was raised by like, you know, 5, then would it be the limit would be infinity, or?
What do you mean, like if it were sine to the 5th?
No, sine plus 5, because that would raise the entire. Right, because the problem would be that.
Like this? That's the argument?
Yeah.
It still doesn't exist, because as this x approaches infinity, it's still, you're asking what's the sign of something that's infinite, and it doesn't flatten out. This would be a shift to the left 5 units. So when we shift sine to the left 5, it doesn't,
right.
like it doesn't change it. You just mean like, what if it were like the sine of x plus 5, like this?
Yeah.
Yeah, so then the whole sine function shifted up, but, you know, just because we shift all of that up, you know, we're not looking at that part, but just because we shift that oscillation up 5 units doesn't mean it doesn't keep doing what it's doing right there.
But if it's like one of those ones that starts shrinking down the oscillation.
Sin x
Yeah.
over x.
Sine x over x, yeah, that would have a limit. Yeah. Yeah. Any other questions?
So, can you explain about like if we can like if we can solve the activity derivative for like the limit, you know what I mean? For like that one,
Yeah.
we can find like the entire derivative, but they give us like the that question. What should we do?
So like we'll have to get through chapter 9 and 10 to talk about how to do that. But again, it's based on the idea of convergence, which is the same idea as convergence in this section. So yeah, I mean, I'll make a note over there on that board. I was kind of getting ahead of ourselves, but this is chapter 10 and 11. Chapter 10 and 11. We'll talk about stuff like that. Ultimately, just like with anything else, it seems like it's very painful to get to the actual destination because you got to talk about so much stuff. But we'll eventually get there. Okay, x ln of 10x from 0 to 1/10. So first rewrite this, and then what's the issue, the 0 or the 1/10?
Why would any of them be a problem? Because can't you take the natural log of 0?
Okay, can we take the natural log of 0?
No.
No, remember, Here's the natural log.
Oh, yeah.
Yeah.
I was thinking 1.
Right, 1. So here, natural log of 0, that's a vertical asymptote. So it's the 0 is the issue, not the 1/10, because the 1/10 natural log is defined at 1. So the 0 is our issue. And it's going to be the limit as a approaches 0 from the
Right side?
right. Yes. Remember, those limits matter. The left from the left or from the right, and you just need to look no further than the first page. One of those functions, we approached something from the left and it was positive infinity. Other, we approached it from the right and it was negative infinity or something like that. So the limits from the left and the right totally matter.
So on the test, don't have to write like the left or right.
Yeah,
Okay.
yeah, I want to see that. I want to see from the left or from the right. It's not just that we're approaching 0. There's an asymptote there, and we have to approach it from one. We're only allowed to approach it from one direction. Okay, how are we going to find the antiderivative of x ln of 10x?
You.
Yeah, that's integration by parts. We've got a product, integration by parts for products. So integration by parts. And again, let's just find the antiderivative first, and then we'll plug in the bounds and then compute the limit, because we get a partial function where it's u times v evaluated from a to 1/10 minus another integral from a to 1/10. So let's just find the antiderivative first. We need to identify u and our dv. So what are we going to let u be?
Natural log of 10x.
Natural log of 10x. dv is going to be then x dx. Du rather, the derivative of u, derivative of natural log of 10x would be
10 over
10 over
1x. 1 over x.
1 over x, because it's 10 over 10x, right? 1 over x dx. And then v is the antiderivative of x, so x squared over 2. All right. So we're just write it here. We're just working this problem. Antiderivative of x ln of 10x first, and then we'll sort of fit all the pieces in. It's u times v. Minus the integral of v du. So we have x squared over 2 times 1 over x. We get x over 2. X over 2. So one round of synthetic division, or sorry, one round of integration by parts, synthetic division. One round of integration by parts gets the job done, more or less. We have this. Minus antiderivative of x, again, x squared over 2, or 1/4 x squared. Really we have a plus c, but it's a definite integral. We're not going to worry about the constant. Okay, so we found antiderivative, then we're going to compute this thing. Wait, I think it was a. I forget. 1/10. Wrong problem. gonna be the limit as a approaches 0 from the right. X squared over 2 ln of 10x minus 1 over 4x squared. All right, any questions on where we're at, what we've done? All right, plugging in 1/10. We have 1 over 100 times 2. Natural log of, well, I guess natural log of 1. So that's really, minus 1 over 400. Minus a, so a squared over 2 ln of 10a minus 1/4 a squared. And, you know, it's the limit of all of this, but the limit only operates on our second, or our last two terms. So we get the ln of 0 times of all of that stuff. Or sorry, the ln of 1 rather is 0 times 1 over 200. That's 0 minus 1/400. We have minus this limit as a approaches 0 from the right on this thing here. Right. So we got a finite number here, but we've got to determine what this limit is. I think it's easy enough with this piece here, 1 over 4a squared. Of course, that's going to approach 0 as a approaches 0. So let's compute this other limit here below. The limit as a approaches 0 from the right. We have a squared over 2, natural log of 10 times a. So as a approaches 0, what is our limit? 0 times negative infinity, right? So if we directly substitute here, this limit becomes 0 times negative infinity. So that's sort of one of those one-offs. It's not L'Hopital's rule directly, but it is related to L'Hopital's rule. Those indeterminate products like that, we can always rewrite them so that they relate back to L'Hopital's rule. So again, we're not applying L'Hopital's rule directly to this function because it's it's an indeterminate product. We need this function represented as a quotient, 0 over 0 or infinity over infinity, before you apply L'Hopital's rule to that. So we need to rewrite our function so that it's a quotient, an equivalent quotient. So we're going to leave ln alone, and what do we have to do? Notice that 1/2, it's sort of in the way, so you can just put it out front. So we have to write that a squared ln of 10a is the same thing as the ln of 10a divided by what?
1 over a squared.
Yeah, the reciprocal 1 over a squared. That's how you write any any product as a quotient, right? 2 times 3 is really 2 divided by 1/3. or 3 divided by 1/2. So you just reciprocate one of those. And if you've looked over L'Hopital's rule enough, you know that it's easier to leave the logarithms alone and reciprocate the sort of the algebraic functions. So if you forgot that, then here's your reminder. Leave logarithms alone, we're going to reciprocate the algebraic function. Now the limit as a approaches 0, what do we end up with here? Negative infinity over, oh sorry, I just didn't catch it.
Oh, infinity.
Yeah, infinity. So that's something you can apply L'Hopital's rule to.
Does it matter that there's a negative on top or no?
It does not,
Okay.
yeah. Yeah, L'Hopital's rule, infinity over infinity, is any combination of infinity and negative infinity. So from this point here, we're going to apply L'Hopital's rule to that quotient. Oh, I'm sorry. As a approaches 0. Right. You got to take the derivative of the natural log of 10a, which we already have, more or less. Derivative with respect to a. So 1 over 10a times 10 is 1 over a. And the derivative of 1 over a squared with respect to a would give us what? Negative 1 over a? That's the antiderivative, yeah.
It's negative 2 over 8.
Negative 2 over a cubed derivative. So okay, we rewrote it as a quotient. It's something we apply L'Hopital's rule directly, and we get this thing. Remember, it's always L'Hopital's rule, then you simplify before you compute the limit again. So we want to simplify this first. Simplify. We have 1/2 the limit as a approaches 0 from the right. And then we've got an a cubed over negative 2a. Or a squared over negative 2. As a approaches 0, we can now see that this does indeed approach 0 times 1/2 is 0. Any questions on that? So like I said, if you're not familiar, you forgot L'Hopital's rule, you've got to look over that. In chapter 10 and 11, it comes up again. So we're going to go back up here. We now know that this limit approaches 0. So we have 0 minus 1 over 400 minus 0 minus 0. So we've got a finite convergent area. Any questions? Yeah, and the last page is just a summary. What we didn't see was we didn't see situations where it was the integral from negative infinity to positive infinity. And we don't, but we can handle those as well. You just pick some value that's in between. So like you know, you find some value here, the function is defined, and they call that c. And then you integrate from negative infinity up to c, and then c to positive infinity, and then you've got two improper integrals. So that turns into these two things here. But I don't think we have any of those in our homework or our quiz, so. All right, that's 8.9. Any questions? 8, 9? So we'll take a break before we start chapter 9. We've got only 2 sections from chapter 9. You've got a chapter 8 and 9 quiz. So this is still part of our second unit. But chapter 9 is just a really basic introduction to differential equations. In 9.1, we look at verifying solutions, finding general solutions, and solving initial value problems. And then in 9.3, we look at separable differential equations. So that's what we're gonna do after we come back from break.
Fahey? Whatever the hell his name is. Don't take it. If you can, take it to Anthony Smith.
It's only online.
Okay, so the basic ideas here in 9.1, they introduce like what a differential equation is, and so they've given 3 examples, A, B, and C. They're different types of differential equations, and they're sort of classifying them through this paragraph here. So a lot of this terminology, I'm not going to test you on. It's just sort of looking at each one of these A, B, and C and describing what kind of differential equations they are. There's many different kinds of differential equations: separable, linear, homogeneous, non-homogeneous. And depending on what they are, you have different methods to solve them. But in general, differential equation is, here's an equation involving derivatives. What's the original function that would satisfy the first derivative plus 4 times the function would give us cosine, and that's the idea of any differential equation. Some of the ones we look at here in 9.1 are really basic, meaning that you've already done them in Calc 1. So just some more stuff, but the main thing that we're solving here in 9.1 that we want to focus on for the exam are the initial value problems. So you're given a derivative or a second derivative and conditions that go along with the function, the first derivative, etc. And then from that, you want to find the original function, which for us just means, or for any situation like that, usually just means antiderivatives solving for C. And so these initial conditions that are given to you allow you to find C. Any of the constants that show up. If you have one derivative, you have one constant. If you're given a second derivative equation, you've got 2 constants ultimately that you have to find, and so forth. So, all of this is very technical, and I'll leave that reading to you. Like I said, we're not really going in depth for any of this, so I'm not going to test you over any of that kind of stuff. So the first thing we're going to look at, though, is verifying general solutions. So we're going to be given a differential equation, which is this thing right here. That's our differential equation, and the claim is that this y of t, this function here of t, is the solution. So just like in an algebraic procedure, really, if you have an equation and someone says that this thing is a solution, you just plug your solution into the equation. Is it a true statement? Yes. Then it's a solution. Is it a false statement? Then it's not a solution. Okay. So we've got to verify that the derivative of our function plus 5 times our function is equal to 0. So what we're trying to verify is that this y of t is a solution to that differential equation. So we have to find y prime because we have to add 5 times y to that to verify if it's 0. So the derivative of y, the derivative of some constant times e to the negative 5t would be what? What's the derivative of y?
Negative 5e to the 5t times the constant.
Yeah, negative 5c times e to the negative 5t. This is derivative with respect to t, right? That's our independent variable. All right, and so we want to know also what's 5 times y of t. So we'll do that here. 5 times y of t is 5c e to the negative 5t. And then we want to know what happens when we add these two things. So if I add these two things together, my left-hand side is what I'm trying to verify, y prime of t plus 5y of t. And negative 5c e to the power plus 5c e to that power is 0. So that's our verification that that's an actual solution. Pretty straightforward. These kinds of things where you verify solutions aren't going to be on the exam. There's so much content from 8.1 to 8.9 that we're only going to have one question on the exam from 9.1 and one question from 9.3. But there are some in your homework that ask you to verify. Does anyone have any questions on that? Okay. Another example. I guess I could have scooted this stuff out a little bit, but here's the differential equation. And we want to verify that this thing right here is a solution. That function is a solution to that differential equation. So our differential equation involves u of t, which we're given, and it also involves u double prime, so we need to find u double prime. So we have u of t, derivative of u with respect to t, 5c1 t to the 4th minus 4c2 t to the negative 5 minus 3t squared. Okay, u double prime is 20 times c1 t cubed plus 20 c2 t to the negative 6 minus 6t. All right. So our equation involves a t squared times u double prime. So we're going to compute that t squared times u double prime. We have 20 c1 t to the 5th plus 20 c2 t to the negative 4 minus 6t cubed. Okay, so we have this part. Now we need to multiply u of t by negative 20 and add these two results to see if they actually are 14t cubed. So let's just put here negative 20 u of t. And again, you do these however you want to do these, but this is how we're going to do them. So negative 20 times the u of t given. We have negative 20 times c1 t to the 5th. Negative 20 c2 t to the negative 4. And negative 20 sorry, positive 20 t cubed. So we're just going to combine these two things. We got t squared u double prime minus 20 u of t equals, we got 0 there, we've got 0 there, we've got minus 6t cubed plus 20t cubed for a 14t cubed. So if you take differential equations, most of you will, since you're engineers, it's very in depth. It's got its own branch of mathematics. It's like kind of related to calculus, but kind of different. So it's quite heavy. It's very involved, and so like Calc 1 and Calc 2 in this like two-dimensional plane is to differential equations, is to Calc 3 is to partial differential equations, which is even harder. But verifying things are solutions, pretty straightforward. Does anyone have any questions? Then we can also verify solutions to initial value problems. After we verify a few of these, we're going to look at initial value problems themselves. And those are the initial, solving an initial value problem is what we want to focus on, especially for the exam in 9.1's material. So here we have our differential equation. We have our proposed solution, and then we have our initial conditions. Initial conditions, differential equation, and our solution. So like if in differential equations class, they would give you the differential equation and the initial conditions, and they would say find y of t. So you have all these methods to solve those. Okay. So verifying, similar to how we verified previously, but you also want to verify that the initial conditions are actually true as well. So is y evaluated at 0 equal to -3? And maybe you can just do this by inspection, but so y evaluated at t being 0, that should equal 3. -3, yeah, thank you. Cosine of 0 is 1 times -3, -3. So that initial condition checks out. Second initial condition, it's on the derivative, so we need to find the derivative and then make sure that initial condition is working for the derivative. So our second step, find y prime of t. Y prime of t would be what?
I think it's 9 sines cosine, or 9 sines 3t.
9 sine of 3t. Yes, 9 sine of 3t. And then we want to verify, does y prime evaluated at 0 give us 0? Yep. 0 equals 0. Okay, so we verified the initial conditions, and that's really the only other added step when we have initial conditions. To verify the differential equation, we're gonna just do what we did in the first two examples. So with y double prime times 9y. So the third thing we need to look for, first of all, is the second derivative. So the derivative of 9 sine 3t would be 27 cosine of 3t. So y double prime plus 9y. So y double prime, here's 9 times y of t. Y of t was negative 3 cosine 3t, so negative 27 cosine of 3t. We want to verify that those two things added together give us 0, which we can clearly see. Okay, so we verified the solution and the initial conditions. So questions on that? All right. Finding general solutions. This is exam material here. So find the general solutions. Use C, C1, C2 to denote arbitrary constants. So what we're given is, we're given the fact that the derivative is this function, 12t to the fifth, etc. What we want to find is y prime. So you're given this, we want to find y of t, not y prime. Given y prime, find y. So y of t is the antiderivative of y prime of t. dt. But we know that when we integrate, we get some arbitrary constant. So it's y prime of t plus some constant, and then we use, if we have initial conditions, we would use them to find c. Here we don't. So our y prime of t, when we integrate it, we're just going to have some function plus c, and that's our general solution. Okay. So we have the antiderivative of this function. And then that's going to give us our, y prime of t with our constant. So we have, sorry, not 6, that's the power. 2t to the 6th minus 4t to the 5th plus 2t plus 6t to the negative 1 plus c. Since the c's over there, that's our y prime, or that's our y of t. Just basically boils down to being able to compute antiderivatives. Okay. Any questions on that? Those things you saw in Calc 1, so hopefully this is more of a refresher than it is anything else. Example 5, we are given the second derivative, so we have to integrate twice to find y of t. So y prime of t is the antiderivative of the second derivative. So that's gonna give us what?
Five e to the 3t minus 1 fourth cosine of 4t plus c.
Do you agree?
Alright. So it's a negative and positive.
Yeah. 'Cause derivative of sine is cosine, derivative, antiderivative is negative. So that's our y prime. We have to integrate that again to get y. To integrate all of that with even our constant with respect to t. So this is where, like, you know, this and when we're separating differential equations, it's where it makes a lot of sense to keep track of your constants for sure. Okay, antiderivative of this would be what? 5/3 e to the 3t
Minus 1/8 sine of 4t.
minus,
Or 1/16.
yeah, 1/16.
Good.
Minus 4t plus,
CX.
C1t
C. Yeah, so this will still be c
plus c.
times c plus another constant, right? Another constant of integration here we'll call c1.
Oh, so you don't keep the first one as c1?
No, because that's now we're antiderivative with respect to t on that.
So as you keep going, the new ones get
Yeah,
different.
right,
Okay.
exactly. And if we integrate that again, that'll be c over 2t squared plus c1t if we had to integrate again. Okay, so that's the function whose general solution to that differential equation. You know, we can verify, is that a solution to the differential equation? Just find the second derivative. And then when we look at these with initial conditions, the only thing that changes is that after each round, we use the initial conditions to figure out exactly what those constants are. So that's like the only difference. Does anyone have any questions? Solve the following initial value problems. We have two of these. Yeah, for one, first derivative and second derivative here. Antiderivative of sine t plus cosine 2t. Antiderivative of sine is what?
Negative cosine.
Negative cosine.
T. Antiderivative of cosine 2t.
One half
Sine 2t. And we have our constant here. So that is y of t. You know, these points here in this space are t comma y. So you have this right here, this kind of situation. So when we evaluate this function at 0, it should equal 4. y of 0 should be 4. Gives us a means to solve for C. So we have -1, we have 0, C is equal to 4. C has to equal 5. So then we just put that back in for our C, and that's our specific solution. So our actual solution, y of t, negative cosine t, plus 1/2 sine of 2t, plus 5. Any questions? So that's really as involved as 9-1 gets. Hopefully it's 3 points on the exam. All right, so second derivative here, we've got an initial condition on the function and the derivative itself. That way we can find both constants. So our first derivative, u prime, is the antiderivative of u double prime with respect to t. So antiderivative for e to the 2x minus 8e to the negative 2x dx. Oops, my bad. So u prime is what? What's the antiderivative of 4e to the 2x? 2e to the 2x minus the antiderivative of 8e to the negative 2x
Plus 4e to the negative 2.
plus 4e to the negative 2x. Antiderivative, we get a constant. And then we're going to use the fact that u prime of 0 is equal to 3. And our space is the xu coordinate system. Okay, so we have 2 times e to the 2 times 0, 4 times e to the 2, negative 2, sorry, times 0 plus c. All of that should be 3. E to the 0 is 1 times 2, 1 times 4, plus c, has to be 3. So c has to be minus 3. Just to save space, we'll just write it up here. U prime is 2e to the 2x plus 4e to the negative 2x minus 3. So then we do all of that over again with our other initial condition to figure out what u of x is. antiderivative of u prime. Gives us our u of x. So e to the 2x, antiderivative of 2e to the 2x. Antiderivative of 4e to the negative 2x. Minus 2e to the negative 2x. And the antiderivative of negative 3. Antiderivative involves another constant. So call it C1 or C2, whatever you want to call it. And then we were given that u of 0 is equal to 1.
Could you just call it C since there's no other C in that equation? Or would that be
Yeah, you can call it
totally-
C,
Okay.
because we don't have another C. Well, I mean, technically our C was 3, negative 3, so.
Okay. Is it technically wrong?
Yeah, it is. Because C is reserved for something else. But I'm not nitpicky about that kind of stuff. You should be careful, but.
I just kind of saw there was no other C, so in this part of the problem.
Yeah, this part, right, yeah. And that's totally logical. U of 0 equals 1. And then that's going to give us this constant here. So. Okay, so we have 1 e to the 0 minus e to the 0 times 2 minus 0 plus C1 is equal to 1. Minus 1 is plus 1. So second constant is 2, therefore our function was whatever this was. E to the 2x minus 2e to the negative 2x minus 3x plus c, plus 2. Plus 2. Easy enough? Any questions on that one? Okay, the last page, I just took this from your textbook. A little bit of it got cut off. My apologies. But it's really like nothing we need to worry about. Nothing that most of you would ever see. But it is worthy to mention that there are instances where the general solutions aren't unique, or the solutions to differential equations rather aren't unique. And you might not be sure whether they exist. So sometimes you can guarantee that it exists, but not find the solution. You can guarantee that something's unique, but combination of both of those, it's like they say, it's a difficult thing to do. For us, we don't have to worry about that because everything we see exists and is unique. So for those of you interested, it's just there as a note, but nothing we really have to worry about. So that's the initial value problems. In 9.3, we're looking at separable differential equations. Now this is probably new for us, but at this point, we don't have a whole lot of techniques. Basically, our techniques to solve differential equations involve antiderivatives. So in 9.3, we just have to figure out how we can rewrite or separate the variables so that we can integrate both sides and then solve. Okay. So the method of separation here with our generic differential equation rather, g of y times y prime equals to h of t. So you have some function of y times the derivative of a function with respect to t equals another function of t. And so that's separated because y prime of t, you want to think about it as the derivative of y with respect to t. And so when we integrate this, I don't have a lot of room, but when we integrate this thing, when we say this is g of y, this function of y, times y prime, which is dy over dt, is equal to h of t. What we can do now is integrate both sides of this with respect to t. And see on the left-hand side, what happens is the differential t divide away. And then on the left-hand side, we just have the antiderivative of a function of y with respect to y equals the antiderivative of a function of t with respect to t. So you can integrate both of those individually to solve for y. So, you know, by and large, some more terminology and stuff, but by and large, the issue with separable differential equations is figuring out how to separate. So when we see something like y prime is equal to y times x squared plus 1, you want the functions of y on the side with y prime. Okay, just like this note here says, we want the function of y's, or with y in it, on the same side as y prime. Once you've done that, you've separated it. So we want this y times this x squared plus 1. We want to separate this equation or solve this equation so that we have y times y prime of x in some version of that, right? So we're just going to divide both sides of our equation by y, or multiply by 1 over y. So if 1 over y times y prime of x is equal to x squared plus 1. And so this is y prime of x. Maybe initially it's helpful to think about that as dy over dx times 1 over y is x squared plus 1. So we've separated function of y attached to y prime, and then we integrate both sides with respect to our variable x. So now, how do I want to say this? Integrate both sides with respect to x. I guess I should probably write some more. And, you know, maybe after we see a couple of these, we won't write all of these steps down, but we're integrating both sides with respect to x. Again, same thing happens here specifically as on the first page. We have the left-hand side is just antiderivative of 1 over y. dy is the antiderivative of, that's x squared plus 1 dx. Does that make sense? Anybody have any questions on what we've done?
How are you integrating the left side in terms of x if there's a differential for the dy and then the dx on the left side?
Say that again, sorry. How are we integrating?
In terms of x on the integral of 1 over y dy.
Yeah, so we're integrating in with respect to x, but since we have this y prime here, that's what's getting rid of that with respect to x part.
Okay, so do we still integrate in terms of y, or do we
Yes.
consider the y a constant and pull it out?
No, because this is integrate with respect to y of 1 over y. Yeah, so, yeah, y is not a constant there. So what is the antiderivative of y, 1 over y with respect to y?
Natural log of absolute value of y.
Yeah, that's the natural log, the absolute value of y.
Would it have been okay to recognize that in the first step?
Um,
That y prime over y is the natural log of y.
Uh-huh, yeah. Yeah, so like, you know, we're just writing this out step by step so you can see exactly what's hafting. But yeah, after you've done a few of these, you're probably just gonna separate in your head and just rewrite that. You're not gonna show all your work to separate. Okay, so natural log of absolute value of y equals to x cubed over 3 plus x plus c. Space. So what we're after then is a solution. What is the function y of x? You've got to solve for y here. I hope I can fit all of this in. So we're exponentiating both sides. E to the ln absolute value of y is the absolute value of y. That's equal to e to all of that as the power. And so like keep the absolute value until you know whether or not, or what kind of function y is. Y is an exponential function. The exponential function is always positive. It's never negative. So at this point, when you see, okay, well, this is our exponential function, you know, I think at that point it's okay, but don't just automatically drop the absolute value. All right, so that's our solution. This is y of x, or y, if you will. Typically, they take it a step further because we have e to this power gets rewritten as y equals to, this is e to the x cubed over 3 plus x power, and then it's multiplied by e to the c. Just by properties of exponents. And then, of course, e to the c is just some constant, right? So we call that a constant. This is a constant. So however you want to, whatever you want to label your constant as, but we have y of x, or y equals e to this power times some constant. I'll just call it capital A. That's the solution to that differential equation.
Cody, so I have a question with this one. So if we have like the, for example, like the y 0, like the x equal 0, and y equal negative 1.
Like that?
Yes.
Uh-huh. So if we had an initial condition on this, would that work? We would have, when x is 0, y is negative. So this y can't be negative.
So that's in my first quiz. I thought on this one, they gave me like this exactly like y for x equal 0 is an equal negative 1.
Okay.
And I put like I can solve that problem, but you know the answer they put the negative. You know, it's like the y equal negative like e over like x or something.
So like this, if a were negative though, then all of this stuff that's positive is now both negative. So like I would say like from, if they give you an initial condition, then this initial condition goes here, and you figure out what c is from there. because we wouldn't be able to write it as a times e to this power, because this would be like e to, I don't know, e squared or something, I don't know, whatever c is. But I would go from the initial condition and plug it into that to figure it out. Because like, does that make sense? I'm not sure I fully
Yes,
understand your
because
question.
this one is on the quiz, like, I saw this one on the quiz, that's why, you know, on the first quiz, I fall on this question. Because
Okay.
that what I thought, let's say that you like, it's like E equal to, the Y equal to E, it's always a positive, but
Okay.
the answer is a negative.
Okay.
That's a
I
problem.
think it was question 10 on the
Number
quiz.
10, I'll
Yes.
check it out, yeah.
Most of the original differential equation, it's defined for negative values of y as well, so it makes sense that in the our solution, the answer would sometimes be negative because it would have the same domain as our initial differential equation.
Yeah. Yeah, so, you know, looking at this, it could be negative, but I would have to look at that specific one.
Yeah, that's the reason, like, I don't know why do they have like, it's like negative E for this, for
Okay.
the number 10, the West
All right.
Coast.
Yeah, I'll check that. Quiz number 10.
Yes.
Is this equation,
Like I've seen this type of equation before, is it like a certain graph? You know, it's called like a certain graph.
Our solution?
Yeah.
Yeah, I don't know.
Exponential population growth can be
Something like
modeled
that.
by that.
Yeah.
That's probably where you've seen it.
Yeah, I don't know like specifically, but you've seen like a times an exponential, constant times an exponential. It's probably,
It was with somewhere like with Martian polynomials.
oh,
But
yeah, that I don't know.
I don't know if it was actually.
Yeah, I'm not sure. Okay, we do have some that are, have initial conditions on them as well. Okay. So we've got example 2, u prime of x is e to the 2x minus u power. We're thinking of whatever we have as prime here, u prime, we want a function of u times u prime before we integrate it. Okay, so in order to separate, we need u times u prime, or a function of u times u prime. So we look at it this. Look at it like that. U prime is this here, properties of exponents, or e to the 2x over e to the u. So then separating it, we're just going to multiply both sides by e to the u. So we have our function of u times u prime, just like in the last example. We had our function of y times y prime. So this is separated. Now we find the antiderivative with respect to what variable? X. Yeah, the input here. So we're going to take the antiderivative with respect to x on both sides. Yeah, maybe you don't have to write all of these steps out, but we're going to show them at least for the first few. So u prime of x times dx just turns into what? Du, right? Because u prime is derivative of the function u with respect to x. This differential and this differential divide out. So we have the antiderivative of e to the u du is equal to the antiderivative of e to the 2x dx. So, you know, both of these get constants when we find the antiderivative. We're just gonna put the constant with the other variable, because we're trying to solve for u. We're trying to figure out what the function of u is, and we'll just put the constants together. This side is e to the u. This side is e to the 2x over 2. And so we have a constant here, we have a constant over here, we put those constants together, you get another constant. So 1/2 e to the 2x plus c is what e to the u is. And then from this point, we have to solve for e to the u, or sorry, solve for u. Or u of x. Okay, so our u is equal to what?
Can you pull out the 1/2 in front of the natural log? It would be like 1/2 natural log of e to the 2x, which you just gave me, x plus c.
No, because in order to get a u here, you have to take the natural log of this side. So that means you have to take the natural log of all of this. So it's this.
So you can't pull out that 1/2.
No, that's u of x. I mean, if there were a rule for the natural log of a sum of two or more things, then yeah, we might could try to manipulate that more. So I don't know, u, it's a function of x, so I guess technically we'll label it u of x. Does anyone have any questions? Okay, we're gonna look at one more. It's an initial value problem. So we've got 2y, y prime equals 3t squared. So do we need to separate that? It's already separated. You've got a function of y times y prime is a function of t. Okay. So we can integrate that as it is. There's no separation needed. It's already separated. So we have the antiderivative of 2y, y prime. Again, we're integrating with respect to t, sorry, not x. Integrating with respect to our variable t. Okay, and that's equal to the antiderivative of 3t squared dt. So, you know, possibly you just start out by saying that the antiderivative of 2y dy is equal to the antiderivative of 3t squared dt. So that's fine if you start out with that after you've separated it. I think after you've done 2 or 4 or 8 or 10 of these things, that you realize what it turns into. So starting with something like that is perfectly fine. Okay. So we have the antiderivative of 2y equals the antiderivative of 3t squared. Okay, so y squared equals t cubed plus c. And solving for y here, we would say, you know, maybe inclined to say that it's the positive and the negative square root of t cubed plus c. Remember, we've got an initial condition which is going to allow us to find c. That initial condition says, the initial condition says it's t comma y our point, so t is 0, y is 9. So the thing that we're looking for at this point, it's a positive y value. We don't need the plus minus square root. Yeah.
Yeah, so
I think you said it earlier, why don't we have a constant on the left side for the left integral?
So yeah,
Is
we
it-
kind of do. We have this constant here,
But it makes a
and this constant of integration
combined.
there. Yeah, and then we
So-
just isolate, because we are just trying to find what y is. So we just put this thing over here,
C2 minus C1 is C.
and then it's just another constant.
Oh, okay, cool.
Yeah, is everybody okay with that? If you want to put the constants with the y's and the t's or whatever, that's totally fine. It's just kind of, I don't know, it's almost redundant. Okay, so we're gonna just say initially that's what it is, but it's actually this based off of the initial condition. Initial condition tells us that y is 9. So y is positive based off of the initial condition. It's y of 0 equals 9. So y is positive. We have our y as a function of t. Square root of t cubed plus c. And we know y evaluated at 0. Key value of 0 is going to give us 9. In other words, we have the square root of c is equal to 9, which means c is 9 squared, 81. Guess I need to leave more space. But we're just going to put that c in for our c right here and have a specific solution. So we have our function y of t is the square root of t cubed plus 81. And that's our solution. Do y'all have any questions on any of that? So I just recommend starting the homework, seeing what you could do.
Yeah.
And next class we'll have to finish 9.3 as well as talk about the exam and review. So also come to class with any homework, quiz, exam questions you might have. See you.